Next, let us introduce the space of compactly supported sections. Let E to X be a vector bundle. Then we define the space of compactly supported sections to be those sections such that support of S is compact. As usual, support of S is those P in X such that S of P is non-zero, and the closure of this. So in particular, we may take E to be the rth exterior bundle of a manifold M, and it is clear that if S is a compactly supported section, then ds is also compactly supported. In fact, support of ds is contained in support of S. Thus we get a map of complexes. So we get a complex first, and a map of complexes. And obviously these diagrams commute. So the cohomology groups of the complex are denoted by H sub C M, and these groups are called the compactly supported cohomology groups. So clearly there is a map from compactly supported cohomology to usual cohomology. If M is compact, then obviously the compactly supported sections are equal to the usual sections, so which implies in this case this natural map is actually an isomorphism. They are both the same. Sorry, there's C. So let us see an example. Let M be equal to R. So consider the map. Consider the complex. So here f is sent to df by dt times dt. Suppose df is 0. This implies f is a constant function which is compactly supported. Which implies that f is 0. Thus, H0 CRR is 0. To compute H1 CRR, it suffices to compute the image of D. The image D of if f is a compactly supported function on R, then df by dt satisfies integral minus infinity to infinity df by dt is equal to 0. So thus, if we consider the functional, from gamma compactly supported to R, which is given by f dt maps to f dt. This is surjective, that is clear. And D of the image of D is contained in the kernel of this map. Let's call this phi. So we claim that the image is equal to kernel phi. So given f in the kernel, define g of t to be equal to minus infinity to t ft dt, fx dx, let's say. This makes sense since F is compactly supported. G is compactly supported. Since F is in the kernel of phi, and dg by dt is equal to F. So this implies that F is in the image D of So this proves that H1, which is by definition kernel of D1 by D0 of is naturally isomorphic to R. And explicitly, the image is given by so in general we cannot pull back compactly supported sections since the inverse image of compact sets need not be compact. If, however, the map is proper, then F upper star, it takes compactly supported cohomology, compactly supported sections to compactly supported sections. Also, if U is an open set, and S is a section which is compactly supported over U, then there is an obvious inclusion where we simply extend the section given by simply extending the section by 0 outside U. So from this, we can deduce a vectorial sequence as follows. Consider the complex the first map is the diagonal extension by zero map. That is, alpha is sent to alpha comma alpha. The second map is beta comma gamma is mapped to beta minus gamma after extending them by 0. It is easy to check that this is a complex. To check exactness, we only need to check surjectivity at so let rho u comma rho v be a partition of unity subordinate to u comma v, and let omega be a global section of M. Then clearly support of rho u omega is contained in U, and support of rho v omega is contained in V. Thus, rho u omega comma minus rho v omega gets mapped to rho u plus rho v, rho u omega plus rho v omega, which is equal to rho u plus rho v omega, which is equal to omega. So this proves surjectivity. Thus we have a short exact sequence of complexes zero, and this implies we get a long exact sequence and so on. So this is the Mayer-Vittori sequence for compactly supported cohomology. So let M be a manifold. Next, we want to compare the compact cohomology of MR and that of M cross R. So earlier we used the pullback. Earlier we used pi upper star to show that these are isomorphic. But now there is no map. However, we can modify the pullback as follows. Let E of t be a smooth function on R which is compactly supported. And such that integral minus infinity to infinity E of t dt is 1. Then we can define by omega maps to, so we denote this map by E lower star omega wedge E of t dt. So since E has compact support, it follows E lower star omega has compact support. Moreover, since t of omega wedge E of t dt is equal to t omega wedge E of t dt, it follows that we get a map of complexes. Okay, so this implies we get this induces map E lower star to H star plus 1 compactly supported M cross R comma R. So we want to show that E lower star is an isomorphism. So for this, we shall define a map of complexes in the other direction. So we will define pi lower star from by integrating along the fibers. So recall that we saw exterior R omega m cross R is isomorphic to exterior R, the pullback, P1 upper star exterior R omega m, direct sum P1 upper star exterior R minus 1 omega, tensor P2 upper star omega R, which is trivial. So this is simply direct sum P1 upper star omega R minus 1 exterior R minus 1 omega m times a dt. So this implies it's isomorphic to m t. So define pi lower star to be 0 on and for omega in the other piece to the following. So suppose on a coordinate open set omega looks like g x comma t dxi which dt, then define pi lower star omega to be equal to minus infinity to infinity gx comma t dt dxi. So this is extended linearly on U and exactly the way we checked. For K, so the homotopy in the previous lecture, we may check that this makes sense globally. So we need to show that pi lower star is a map of complexes. Again, this is a local check, and assume that omega locally is of the type G. Okay, there are two types we need to consider. Omega is equal to G dxi, or it's going to be a finite linear combination of things of this type. Then T of pi lower star omega is equal to 0, since pi lower star omega is 0. And on the other hand, T omega equal to summation I equal to 1 to n Tg by dx. Let's just say J. Dt which dxi, and pi lower star of T omega is equal to, so first term goes to 0, plus the second term is minus infinity to infinity this is equal to 0, since for a fixed x xn, the function g x comma t has complexable. Or omega can be of the form, locally it may be of the form a sum of this type. So then pi lower star omega is minus infinity to infinity dxi T of pi lower star omega is equal to you can just differentiate under the integral and on the other hand T omega is equal to summation j equal to 1 to n we don't need to differentiate with t anymore because gt with gt will be 0, which implies pi lower star t omega so this implies pi lower star is a map of complexes. Next we will show that the map E lower star pi lower star is homotopic to the identity. Before that, so it is clear that for omega, a compactly supported section of exterior R over M, pi lower star of E lower star omega, this is pi lower star of omega which E of t dt, this is equal to integral minus infinity to infinity omega wedge E of t dt. So we just get back omega, hence integral minus infinity to infinity E of t dt is 1. So once we show, so that is this map is E lower star this composite is just the identity. So once we show that the identity is homotopic to E lower star pi lower star, so this will imply that E lower star is an isomorphism. E lower star and pi lower star are isomorphisms. And to show this, we will define a homotopy operator. So as before, K will be defined using local coordinates. So let U x1 xn be a coordinate open set and if, so we start with omega which is compactly supported on all of define k of omega to be 0. For omega of the form g dxi wedge dt, define k of omega to be minus integral minus infinity to t g of x t dxi plus where a of t is the function minus infinity to t e of dt. Let us check that k is a homotopy between 1 and e lower star pi lower star. So we have to check on two kinds of forms. First is when omega is equal of the type g dxi, then e lower star pi lower star omega is 0, since pi lower star omega is 0. Similarly, t of k omega is 0, since k omega is 0. Now let's compute k of d omega, that is equal to k of summation j equal to 1 to n and this is equal to k of minus dg by dt dxi wedge dt, which is equal to integral minus infinity to t dg by dt dt dxi minus a of t minus infinity to infinity dxi. This is equal to g of x comma t dxi minus 0, which is equal to omega. So this implies that 1 minus e lower star pi lower star of omega is equal to kd minus dk of omega. So next let us check on the forms of the type omega is equal to g dxi wedge dt. So here e lower star pi lower star omega is equal to dxi wedge dt. On the other hand, k of d of omega is equal to k of summation j equal to 1 to n dg by dxj dxj wedge dxi wedge dt. The term with the derivative of with respect to t does not appear because dt wedge dt is 0. This is equal to plus a of t, t is minus infinity to infinity, summation is on the whole thing. And similarly we compute t of k omega, that is equal to t of this is equal to and this is equal to omega plus k t omega minus e to a star pi to a star omega. This is omega, this is minus e to a star pi to a star omega. So once again this implies that 1 minus e to a star pi to a star applied on omega is equal to kd minus dk of omega. This implies k is a homotopy operator. Thus, as a result, we get that R, which we already saw, this is isomorphic to H2. And so on. So we see that Hn compactly separable cohomology Rn R is R, and Hi compactly separable cohomology Rn comma R is equal to 0 if I is not equal to n. So we will stop here.